Howdy, and welcome back to your groovy boy, Bo Maths. Today, we are going to be doing some exercises, and these are going to be related to the last lecture we did, which was all about the depth of expression trees. We saw this was a property of expression trees that actually had some really nice connections and insights into basically how many steps we could evaluate an expression in. So we spent a bunch of time looking at that and looking at how maybe we could even rearrange some trees to get even better evaluation times. But today we're going to practice that concept with some interesting problems I prepared for you. So as always, pause the video, try the problems out first. They'll be flashing on the screen momentarily, and then we can go through them together. Question 1. Alright, so question 1 just is a simple find the depth of the following expression trees. So we've got 3 trees here, and we're tasked with finding their depth. So for this, we're going to need to remember what the depth is, and there was a couple ways we could look at it. So the basic definition was the longest path from a number to the top operation node. So if we look at all the paths here, from number 2 to the top operation node, which is the exponentiation node, we have a path of length 2. If we start at the 5, we also have a path of length 2, right? 1, 2, we're just counting the edges. But if we start at the 2, we have a path of only length 1. Since we're taking the longest length path, we are going to get a depth of 2. The other way we could have looked at this is basically how many rows of expressions we have, which is also 2. So the depth of this expression tree is going to be 2. For part B, again, we can look at the longest path, but again, it's usually, as we found, kind of faster to look at the amount of rows of expressions. So this is going to be 1, 2, 3. And again, we see that the longest path would be maybe from this 3 up to this negative sign, so 1, 2, 3. Or from this 3, we also get a path of length 3. But if we look at from this negative 2, 0, or 4, those are paths of length 2. But the longest path is 3, so the depth of our tree is going to be 3. Alright, and for part C, the depth of this tree, once again, it's looking like 2. Actually, from every single number, we get a path of length 2 to the top node, 1, 2, 1, 2, 1, 2, 1, 2. So there's no dispute, the depth of this tree is going to be 2. Alright, so not too bad, right? The depth was a pretty simple concept. What made it more interesting was the applications of it, which we'll get into kind of in these next questions here. But if you need some extra practice for the depth, make your own expression trees and find the depth of those expression trees. Question 2. Okay, so question 2 says make an expression tree for the depths 2, 5, and 0. So this one actually wants us to make an expression tree with a preset depth to it. So if we start with an expression tree of depth 2, the way to make this, and there's infinite possibilities, right? We could choose whatever numbers, whatever operations we want. To an extent, we could also choose kind of what the structure of the tree looks like. But again, if we want a depth 2, we're essentially looking for basically something with 2 rows of operations. So one example of this could be something like, let's maybe take the numbers 3, 4, and 5. And we'll combine the 3 and the 4 through division, let's say. And then maybe we'll multiply that with the 5. And we see here we have 2 rows of operations, which means we have a depth of 2, so we've completed that. But again, try and make your own trees, right? Don't just copy the one I have. There's, again, infinite possibilities for this. Alright, let's look at the depth 5 tree. So we want a tree with depth 5, so that means we want 5 rows of operations. So to do this, let's start with getting some numbers. So let's go 2, 4, 6, 7, 8. And if we ever need more numbers, we can always just add them, right? If we see that these numbers aren't giving us a deep enough depth. So let's just start by doing some combinations. So maybe let's add the 2 and the 4. Again, we can just kind of choose whatever operation nodes we want. Of course, we could combine these in like the same step as well, but it's faster just to kind of, for every operation, introduce a new depth, right? Ultimately, we're just trying to get a depth 5 tree, so we don't need to make it really complicated. The simplest way is just every operation node happens at the next depth level. Maybe I'll do an exponentiation. So we're looking at 4 rows of operations. We're at depth 4 right now. So we need to add another number. Maybe let's add like negative 2. And let's subtract it off. Okay, so that is our depth 5 tree. Basically, the longest path is going to be from this 2 out to the top operation node, and that is a path of length 1, 2, 3, 4, 5, so we have a depth 5 tree. Now, the last one asks us to make a depth 0 tree, which is kind of weird. We know that a depth 1 tree would maybe look something like that, right? Where we have just a distance of 1 from the number to the top operation node, because there's only one row of operations. But depth 0 would basically be, well, there's no rows of operations. So essentially a depth 0 tree would be a node with a number in it and nothing else. There's no operations. And a number can be viewed as a valid expression. We're just not doing anything to this number, right? So this would be a depth 0 expression tree, basically just a plain number. All right, and if you want some extra practice, choose a non-negative whole number and make various expression trees with that depth. The reason it's non-negative is it doesn't really make sense to have a tree with a negative depth. And the reason it's a whole number is it doesn't really make sense to have a tree with a depth of like 1.5. You can't really have half a row of an operation. Question 3. All right, question 3 says, for the trees in part 1, how many steps would it take to evaluate them using the given tree and with no rearrangement? So we saw that we could sometimes rearrange trees to decrease the amount of evaluation steps, but this is saying just using the trees in part 1, so this A, B, and C, how many steps did it take to evaluate them? Well, this is going to be a very fast question because we saw that the depth corresponds to the amount of steps that we can evaluate any of the trees in. So for part A, we already have our answer. We saw the depth was 2, so it can be evaluated in 2 steps. The first step to do the addition, the next step to do the exponentiation. For part B, we had a depth of 3, so that means it can be evaluated in 3 steps. The first step to do this addition for these 3's and to do this division over here. Second step to do this multiplication part, and the last step to do the overall subtraction, right? But that can occur in 3 different steps, where we ultimately just do this plus and this division kind of simultaneously in the first step. So we only really need 3 equal signs. That's kind of what this 3 steps means. And for part C, we saw it had a depth of 2, so once again, this is going to be 2 steps. The first step, we do both of these additions because they're independent, they can be done at the same time. And then we do the exponentiation for the last step. And for extra practice, make your own expression trees and find out how many steps are needed to evaluate them. If you were doing some from part 1 where you kind of made expression trees and found their depth, you can go ahead and do the extra step of converting that depth into the steps, which is just this kind of one-to-one conversion where the depth is always the amount of steps. Question 4. All right, so I think this is kind of a fun question. So the following expression tree evaluates to 1,111. What must be the depth of the tree? So here we see that we're starting with 1 and we're adding it to 1. And then we're adding another 1 in and we're adding another 1 in. And then what this ... means, we've seen it before, right, where we have maybe like a repeating decimal, like 2.3 ... That just means it kind of continues on with the pattern, right? So in this case, the 3 continues on. So over here, what this is saying is that it's continuing on with the pattern of just adding 1 every step, right? Basically, there's kind of an operation node of a plus here that's combining a new 1 in there. And this keeps on going until we eventually stop at this final 1 here that we add onto it. And it's saying that this whole thing is going to evaluate to 1,111. So we don't know on the offset how many kind of operations are in here, how many times we're adding a 1, but we do know that the evaluation tree evaluates to 1,111. And since we're adding 1 every single time, well, if you just add 1 to itself over and over and over again, how many times do you need to do that to get 1,111? Well, 1,111 times, right? If you're adding 1, that's essentially just counting, right? When I do 1, 2, 3, that is me just basically adding 1 to each number. That's what counting is. So to count to 1,111, we need to do 1,111 combinations of 1s. So let's kind of look at what we see here. So when we're at a depth of 1, so this is depth 1, we get to 2, right? 1 plus 1 is 2. When we're at a depth of 2, we get the 2 plus 1, which gives us 3. When we're at a depth of 3, we get the 3 from over here, add the 1, we get 4, right? So at depth 1, we got a 2. At depth 2, we got a 3. At depth 3, we got a 4, right? So if we just continue on this pattern here, we know that we're ending off at 1,111. So what do you think the depth of this expression tree would be then? Well, we notice that the depth is always one less than whatever it's kind of currently evaluating to at that step. So we would expect then the depth to be 1,110, right? Just one less than 1,111. And this hopefully makes sense because we're adding 1,111 ones together, but we're already starting with 1, 1, right? So the amount of additions we do is basically adding on to that 1 we have. So adding on to that 1, we need to only add 1,110 more ones to get to 1,111. So that means the depth of this tree must be 1,110.
Question 5.
All right, question 5 is interesting. It asks us to rearrange the following trees to be depth 3. So whenever we're rearranging trees, kind of one of the big things we wanted to look out for was repeated operations, specifically usually repeated multiplication or repeated addition, because those can be freely rearranged because we know we can multiply or add in whatever order we want to. So for part A here, we've got 3 multiplications in a row. So that's probably an indicator we're going to want to start by trying to just rearrange this subtree that has all this multiplication. And we can do that by doing this 2 times 3 and this 4 times 2 in the same step, and then multiplying those afterwards. And what that's going to do is it's going to take this subtree, which is of depth 3, and it's going to reduce it to a depth of 2. So let's see what I mean here. So we take our numbers 2, -3, 4, and 2, and we're going to combine those through multiplication. And that's going to occur in the same step, right? So we've reduced it to where we're just multiplying one number in at every step to starting off by multiplying both the pairs of numbers and then multiplying those results here. So we've taken this subtree here and we've reduced it to a depth of 2 from a depth of 3. And now all we have to do is take that result and add the 9 to it. And now we've gone from a tree of depth 4 to a tree of depth 3. For part B, it's a little trickier. We see we have a lot of multiplications and divisions kind of switching back and forth. And you might think, okay, this is not really something that we can work with because we don't have a bunch of multiplications in a row. And that's really the only technique we've seen. However, we have seen that we can convert division into multiplication, right? So if we do that, we actually suddenly can get a tree where it's all multiplication, right? So if we do that, we do 4 times 3, and then we're dividing by 5. But what is division by 5 in terms of multiplication? That's multiplying by the reciprocal of 5, right? Division is always multiplying by the reciprocal. And the reciprocal of 5 is a fifth. So we can actually multiply in a 1/5. And then we're multiplying by 2. And then we're dividing by 4. So to convert that into multiplication, we are going to multiply by the reciprocal of 4, which is a quarter. And then lastly, we're dividing by 2. So once again, we're going to multiply by the reciprocal of 2, which is a half. And now we've converted this tree into something where it's all multiplication. And now we can freely restructure this to get a tree that is of depth 3. In the first step, we can do 3 separate operations. So that's quite a condensation already, right? And then we do this multiplication here. And then lastly, we'll do a final multiplication. And boom, we've reduced the tree to be of depth 3. Now, some of you might not be super satisfied with the fact that we've changed some of the number inputs. So there is actually another way we can do this where we keep all of these numbers the exact same. So we're going to start with this 4 times 3. And what we want is to consider these next two here. So this 5 and this 2. So we're dividing by 5 and we're multiplying by 2. But do you think it makes a difference as if I do the result of this and then multiply by 2, or if I divide it by 5? It's not going to matter the order in which I do these. So if I do 4 times 3, which I know is 12, right? So if I do 12 divided by 5, and then I multiply it by 2, that's going to be the same thing as if I did 12 multiplied by 2 and I divided by 5. Because ultimately what we're doing is this division by 5 and this multiplication by 2, that corresponds to multiplying by the fraction of 2/5, right? The multiplication by 2 is the numerator, the division by 5 is the denominator. And same thing over here, this multiplication by 2 and then the division by 5 is basically like multiplying by the fraction 2/5. So what that means then is we can take this 2/5 and we can express that as 2 divided by 5, right? We know that's what fractions are. And then multiplying by that, we get this piece right here. What we've done already is we've taken this dividing by 5 and multiplying by 2, and we've kind of combined it where we noticed, okay, division by 5, multiplication by 2 is the same as multiplying by the fraction 2/5. So what we start with is we take the 2/5 and we express it as 2 divided by 5, and then we multiply it like that. So now what we have to focus on is this dividing by 4, dividing by 2. So if I take a number, and we're going to get some result from over here, right? So I'm just going to take any number, let's say 3. If I divide by 4, and then I divide by 2, well, I know that's the same thing as 3 over 4 divided by 2. But then dividing by 2, that's the same thing as multiplying by the reciprocal, which then gives us 3 over 4 times 2, right? So notice what's happened. This dividing by 4 dividing by 2 has become a product inside of the denominator, right? So what we're going to do is we're going to essentially take this 4 and this 2, since we're dividing by both of them, and we're going to multiply them. Because that's what's occurring in the denominator. And then to actually put them in the denominator, we're going to take this whole result here, and we're going to divide it by that denominator, which is the product of 4 times 2. And now we've reduced our tree to be of depth 3. And I think this one's a little more satisfying because we haven't changed any of our number inputs. It's more complicated to get here, right? This was easier. We just simply take the reciprocals of everything and then we rearrange all the multiplications. But this one I feel like almost respects this a little more because we keep all of our original numbers and we're still using some division. But it is trickier. So I encourage you to really think about each and every one of these steps. Just to recap, we started with a 4 times 3, kept that as normal. But then dividing by 5 and multiplying by 2, that's the same thing as multiplying by the fraction 2/5, right? Because we have a division piece and we have a multiplication piece. So in that situation, we express that fraction as 2 divided by 5. And then we're going to multiply that in. So that's this blue piece right here. And then for the pink piece, or for the dividing by 4, dividing by 2, if I take some number, which I just arbitrarily chose 3. We could have taken 10 or 15 or whatever. But the point is, dividing by 4 and dividing by 2, what that ultimately becomes is we're putting the 4 and the 2 in the denominator, and they're being combined in the denominator through multiplication. And since we have that, we can express the 4 times 2 as kind of part of this first row of operations, and then divide that out afterwards, and we get the same thing. And if you're a little confused on some of these steps, I would encourage you to go check out some of the videos that we have on fractions, in particular, the ones on dividing by fractions.
Question 6.
All right, on to the last problem here. So this says, what's the largest and smallest depth for a tree with 4 number inputs? So this is basically saying if I have 4 numbers right here, whatever we choose them to be, what's the largest and smallest depth of the tree? So what's the tree that we can construct from these 4 numbers that has the largest depth, and what's the tree we construct from these that has the smallest depth? So to get the largest depth, essentially the way that can occur is by only doing one operation per row, right? Because one operation per row ensures that every operation we do is expanding the depth. So if we do an operation node right here, and we combine these two, that's the only operation we're putting on that depth. And then next up, we're going to put an operation right here. Once again, that's a new operation we're putting on that depth. And then lastly, we're putting an operation right here. So that's even a new operation we're putting on that depth. So we're adding a new depth with every single operation, and that's how we ensure we get the largest depth. So what we end up getting is a depth of 3 tree. Okay? So we ensure it's the largest depth by adding only one operation node per step. And to get the smallest depth, we basically want to do as many operation nodes as possible per step. That's going to minimize the depth of this tree. Once again, if we start with 4 number nodes, what's the most amount of steps we can do here? Well, we can combine these 2 numbers, and we can combine these two numbers in the same step. So this is the most amount of operations we can do in this single step. And then we can combine these two subtrees with a final operation node, so we get a depth 2 tree as being our smallest depth. So we ensure it's the smallest depth by doing as many operations as possible in each step. So that was for 4 inputs. What about for 3? Well, we're going to want to follow a similar philosophy, right? To ensure it's the largest depth, we add only 1 operation node per step, and to ensure it's the smallest depth, we add as many operations as possible in each step. So we have 3 inputs here, and so to add only 1 operation per step, we're going to get a tree that looks like this, and this has a depth of 2. So depth 2 tree is our largest depth. But if we go to make a smallest depth, can we do more than 1 operation in this first step? Well, the answer is no, right? We've already used these 2 numbers in their operation here. So what that then means then is that this can't be combined with anything else until the next step. There's no other numbers for it to be combined with. So we actually also get that the depth 2 tree is our smallest depth as well. So this is an interesting kind of fact about 3 inputs, is that you can only get a depth 2 tree. The only other possibility is basically to kind of mirror this tree and get a tree that looks like this. Right? These are the only 2 structures that we can get for 3 inputs for an expression tree. Both of them have a depth of 2, so that's both our largest and our smallest depth. But once we go above 3 inputs, like 4 inputs and beyond, we're actually going to get a difference between the largest depth and the smallest depth because we have a lot more possibilities. So if you want some more practice, I encourage you to look at more inputs, right? What about like 5 inputs or 6 inputs? Can you find the largest depth and the smallest depth by kind of using these rules of thumb here? Concluding thoughts. Okay, so that's going to do it for me today. I hope you found this video useful and interesting. I think there's a lot of really fascinating ideas that we can do with these expression trees. And indeed, whenever it comes to just tree structures in general, there's a lot of interesting math that can be done. It's usually done in more complex situations. But I hope you're kind of getting an idea for the interesting intricacies that these tree structures can have. And I think this was a nice little exploration into that topic that also connects with the order of operations things that we've been doing. So without further ado, that's going to do it for me today. You have a good one, you stay groovy, and I'm going to see you in that next Bo Maths episode.
Bo Maths.